Hello, and welcome to C++ Software Security Sins. My name is Mary Kelly, and I am a software consultant here at Embarcadero. This session on software security sins relating to C++ is a really fascinating topic and a fundamental element for any developers who want to create secure software for today's consumers. With the vast number of threats that pressure developers and organizations, there is no greater importance than to ensure that the applications you use and build are as secure as you can make them. So let's get to a few of the sins that plague C++ applications today. Now, we have a lot to cover today on our agenda. First off, I'm going to speak to the importance of software security and some of the consequences. Then we're going to go through some of the C and C++ language specific implementation issues, such as buffer overruns, format string problems, integer overflows, and some C++ catastrophes. So to get us started, what exactly is software security? Well, software security is this idea of building and implementing your software so that it continues to work correctly even when under attack. So the aim is to avoid these vulnerabilities by addressing security from the early stages of software development and focusing in on the code of your applications. Now, software security is also considered to be everyone's job. And with the new threats that emerge every day compounding on the flaws and the bugs that are in our current software systems, it's a really demanding area that requires us to rethink how we design our software. Companies and organizations today are relying more and more on software for the digitization of information and services that consumers use every day. And despite the growth and stories we hear about, we don't really think every day about the protocols around application security for the entire software development lifecycle. We've come a really long way in building secure applications by knowing and understanding a lot of the intricacies of C++ and by providing features in the standard for enabling software security. But I will be the first to admit that writing secure code is not the easiest task, and getting a handle on what those newer features can solve or what additional vulnerabilities they can introduce can be a daunting idea. While there is the white box security technique, a method where an engineer sits there and goes line by line manually through your source code looking for security flaws, the security vulnerabilities out there are a result of code errors that usually go undetected in the earliest parts of the development lifecycle. So this means that the applications and software that you provide that are essential to the success of your business can be at risk for a data breach due to a single line of unchecked code. For example, mobile applications. They tend to be the weakest link because we're typically sloppier about securing them, especially when we forget that we might be using open source components or other third-party software to speed up our development process. We leave ourselves open to client-side injection, poor authorization handling, and even broken cryptography when building mobile applications, since they aren't expected to stay online at all times. So what happens if you're offline, if you allow a user to log in when offline? An attacker can brute force their way through the login, make some arbitrary operations to your app, and then somehow you end up giving a typical user super admin privileges to your backend server. Of course, there is no such thing as completely secure software, but there are always measures that we can take to reduce the likelihood of vulnerabilities. In the case of mobile devices, we could limit the login to an online mode only, or encrypt the app data to only work under specific operations. When it comes to the consequences of software security, the question is, what is valuable to you? And that's a pretty simple answer. Data, information. That's the most valuable asset that any organization has. Information gives us that competitive edge to be at the top of our marketplace or niche. Whether you're an enterprise or a small team, software security is essential. So if our services and software are at risk, then why would we not take the time to secure our code? We hear about the consequences all the time: data breaches, identity theft, bad reputation, lawsuits, loss in revenue. Think about Target from a couple of years ago. They've been set out to pay $18.5 million to the 40 million or so people who were affected by their data breach back in 2013. You don't just bounce back after a couple of months when you get your identity stolen. It all compounds. You don't just get one, you tend to deal with them all. Data breaches can lead to bad perception and legal issues for your organization, and can end up paying a lot of money in terms of the notice and the patches that you have to distribute. Of course, security and system administrators then have to deal with all the extra hours implementing those patches, all while hoping that their consumer software and systems aren't also compromised by any attackers who might have happened upon this exploit. Your attacker has a goal in mind. They want to take over the target machine and probably do something malicious. They could execute arbitrary code on that machine by hijacking your application control flow, or overwriting your heap or stack contents by writing extra bytes. So let's take a look at some C++ sins and see if we can't show you how to fix them. First on our list is buffer overruns. Now, some companies will choose to use automated tools for code audits, but sometimes they don't find all the problems with the source code. So getting back to the basics, let's talk about buffer overruns. Buffer overruns have been around for a pretty long time, really identified all the way back to the 1960s, and are still considered to be one of the more common exploits in C++ programming. So what is a buffer? A buffer is an allocation in memory, some block, kind of like an array, but it's called a buffer. It's just this temporary space that you store values in the computer's RAM. And a buffer overrun is like taking an array of a fixed size and overflowing the bounds of that array. When we expect that our input will be a certain size and we create the buffer to that size, then a running program that attempts to write data outside of this allocated space, it ends up overwriting the program's executable code, and this can cause the application to become unstable, resulting in program crashes, memory access errors, or even corrupted data. Now, you may remember a bug that was discovered a few years ago called Heartbleed. Now, that was a buffer overrun problem. The gist of it was that you would take a request and say, I know that my value has 8 bytes, but I expect 100 or 200 back. So it would read everything in the first 8 and then copy the rest of the bytes into the buffer, sending it back to overflow said buffer and leak contents from the user's memory, bytes at a time. And in the case of Heartbleed, the information leaked included names and passwords of the consumers using the sites that implemented the OpenSSL library. So let's take a look at an example. Now this is a really basic, old-fashioned, and kind of classic buffer overflow example. So just to say that in modern C++, we tend to be able to avoid, or at least reduce, the likelihood of some of the pitfalls that I'm going to be showing today due to some of the new features in C++ 11, 14, and 17. Now, all I have is a couple of different variables, but they differ between the size of the data being stored in each variable. And as you can see, I'm not checking to see if a string is too long or if my buffer's too small. And since I'm not checking the buffer size, when I go to add data to one buffer, if it's too much or too big, then I end up overflowing my buffer. So this is really just a basic example, and I'm going to move forward then to a more current example of a buffer overflow. So let's say we have an application that asks you to log in and add the username. It has to be between 18 and 28 characters, all right? So I'm going to test it out with 15 or 16 errors and see what I get. Whoops, I get an error saying that I have to have a minimum of 18 characters. Now, as a good hacker, I would try to manipulate this. So I'm going to go ahead and type in my 28 characters, and then I'm going to add in a few commands or some other code. Now in this case, I type Mary Kelly software consultant, run DLL 32 $20 shell.dll command prompt. This input has two options. Either the application will filter my code, or it will fail and pass to the shell for execution. If my code is filtered, then the developer went and did their job and said, there's a chance that someone could add more code to the username, so let's filter it after the 28 characters and send a message back to the user saying, hey, you have more than 28 characters here. Say the application didn't filter my input. This buffer overrun occurred when the application failed to check my input length and then put all the data on the stack. So the application reads the first 28 characters, but starting at character 29, it's just somewhere waiting within the stack to be executed. When it finds either a compiler error or maybe even an OS exploit, starting at character 29, that code gets executed. You might think that security here is really simple to implement to prevent a buffer overload, and it is. This buffer overload exists really because of a design flaw or someone just not thinking ahead. As to some solutions on fixing buffer overruns, there are quite a few. First off, comment your code. It really is the easiest way to know when you may have introduced any bugs or problems into your code from the beginning. Check over your code periodically for buffer overruns. I mentioned earlier that a lot of organizations choose to use automated tools and techniques for discovering overruns. One of those happens to be fuzz testing. It's a technique that provides random or invalid data to an application, and then the program is monitored for errors, memory leaks, and so on. This is a great way to expose bugs and can also assist in validating static analysis reports. Avoid library functions that aren't bounds checked. For a long time now, it's been recommended that developers avoid standard library functions that aren't bounds checked. So examples would include gets, scanf, strcpy, any data type libraries that automatically help with buffer management, including bounds checking, can reduce the occurrence and the impact of buffer overloads and could easily provide the majority of the cover that you need to implement. And last but not least, use the C++ standards library and the standard template libraries. C and C++ are both very vulnerable to buffer overflows since they allow direct access to memory. The standard C++ libraries and the STL provide some ways to both buffer data and perform bounds checking when you explicitly call for checks when accessing data. While not as well known as buffer overflows, format string vulnerabilities or attacks have been known to exist for the last 2 or so decades in C++. This vulnerability is named because of the printf family library functions that are part of the standard C library. Format strings, as we know them, are just strings made up of characters with a special format string identifier, and they're one of the first arguments used in printf functions. They use the format identifier to dictate how data will be formatted. When using format string, the %sign begins a conversion specification, and just after is where you apply the formatting parameter for the data type. For example, this snippet prints out a record consisting of a person's name and age. In this case, the first argument is a string and the second is an integer. Now, this sounds pretty simple, and you might not think that anything could go wrong, but a misunderstanding or an attack from a user, for instance, could lead to very serious vulnerabilities. Looking at the following two functions, they look pretty similar. On the first two lines, they're actually identical. They're both allocating a character buffer on the stack and calling fgets to read into it. The real difference is in our printf statement. Our first function doesn't use a format string at all. And we might think, well, buffer is a string in each of these cases, so why do I need a format string? In our second function, we call %s as a format string prior to printing buffer. And an important part of using a format string is that buffer itself might contain format specifiers. In our first case, if it does, then those specifiers will be interpreted, and if an attacker can control the format string, then it can work to their advantage, where they could end up overflowing our buffer or roll back up the stack and control the location that's being written. And in our second case, those specifiers just get printed out on the screen. Format string vulnerabilities result from getting data from an untrusted and unvalidated source, usually a user or even read in through a file. So the first rule is don't pass input from a user directly to a formatting function, and make sure that you do this during all formatted output handling. If you want to use printf, make sure that you add the format string identifier before you print your input. If an attacker gains access, they could execute arbitrary code that could output to a log file or even eliminate their own trace of the hack. If you can avoid using the functions of the printf family, then do it. Printf adds to the size of your application, for instance, since it needs to support all different format strings as defined by the ANSI library standard. So even if you're not using them in your program, they're still there. Now, there is an alternative, and that's using the stream operators instead. We are, after all, C++ programmers, so let's use some real C++, not C. We know what an integer is. It's a whole number. It can be positive or negative. We don't really care. Now, within our software, we put a boundary on the variable, and this provides a fixed range for storing our integers. Now, that's all fine and good, but what happens when your results go beyond the max and min values assigned? An integer overflow occurs when an integer is increased beyond the bounds of the maximum value or decreased beyond the minimum value. For instance, take a byte. Its max value is 255 because of 2 to the 8th power. Now, if we tried to express 275 in that single byte, we would get an integer overflow. Now, C and C++ can be considered to be some of the most dangerous languages when it comes to integer overflows. The effects can vary from random crashes and logic errors to escalation of privileges and even code injection. The error can really be just about anything from under-allocating to allocating 0 bytes. Since C and C++ are everywhere, even if you're spending more time coding in higher level languages, when you access objects that were written in C or C++, if you make errors in your calls, you could still end up with an integer overflow. Now, integers in C++ are either signed or unsigned types. Signed types represent positive and negative values, while unsigned types range from 0 to the max of the type's size. Since integers are numbers and numbers usually mean math, we can use basic algebra and our understanding of binary to work out our allocation for understanding how integers work to get an overflow. Doing the math is also the easiest way to determine how to prevent an integer overflow. So let's take a look. We know that if the size of a data type is n bytes, then it can store 2 to the 8n different values, and that this is the data type's range. So if we have an unsigned data type of n bytes, then its range is from 0 to 2 to the 8n minus 1. And a signed type of n bytes is -2 to the 8n minus 1 to 8n minus 1 minus 1. So a short, which is usually 2 bytes, ranges from -32,768 to 32,767, and an unsigned short ranges from 0 to 65,535. So let's demonstrate the math to an integer overflow. Consider a data type var_t of 1 byte, so the range is 256. Now this signed variable is a and b, and the unsigned variable is c and d. If c is 200 and d is set to 100, then in mathematics, c plus d equals 300, which is more than the max value of 255. Now, since 300 is more than a byte, that higher value will be rejected, and c plus d would now read out as 44. So 200 plus 100 equals 44. Now, note that the reason that we get the response of 44 is because 44 is equal to 300 minus 256, which is the range of our byte. This is an example of an unsigned overflow, where the value couldn't be stored in the available number of bytes. So in these sort of overflows, the result is moduloed by the range, in this case again, 256. Now if A is equal to 100 and B is equal to 50, then A plus B equals 150, which is again more than our max value of 127. So instead, A plus B would actually return as -106. Now the reason for this is because -106 is equal to 150 minus 256, which is our range. And this is an example of a signed overflow, where the result is again moduloed by the range of 256. Addition overflow only occurs when the sign of the numbers added together are the same, which is always the case when working with unsigned integers, meaning that it can be a little bit easier to detect signed overflow since the operand is the opposite of the sign. And something else that's also really cool about overflows is that division and modulo can't actually generate overflows. When it comes to integer overflows, you really have to study the problem to understand what's happening and why. Integer overflows have to be understood from the operands because we're still very limited in what we can do about them since they're hard to detect after the fact. I mentioned earlier that the effects of integer overflows can vary greatly, and this is because they're classified as undefined behavior. The C++ standard defines undefined behavior as rendering the entire program meaningless if certain rules of the language are violated. Now, there are two views on undefined behavior. One is that it's specific to special cases or circumstances, such as hardware, and the other is that anything can really happen. So if a problem is going to arise, it probably will, and it'll be when you least expect it to. A tip to help with correcting integer overflows includes using unsigned numbers whenever possible. There's really no reason to use a signed integer to allocate memory, and the C++ standard also provides you with size_t type for sizes. It is also a lot easier to work with and verify unsigned integers compared to signed integers. C++ as a language has a lot of nuances that many people don't really understand unless they are C++ programmers. And it's not really the most forgiving of languages when you can make these very subtle mistakes and flaws that can be difficult to correct for both yourself and for others to audit. Bugs created with C++ can lead directly to running arbitrary or exploitable code and can end up changing your program flow. So this last umbrella sin of catastrophes I've chosen to break down into a few sections. The general rule of thumb has been that you only apply delete to memory that came from new. So if the new of an array of objects was used, then you must use the array form of delete to match. Now, since C++11, it isn't really recommended anymore to use new and delete unless you're writing library code. The reason I say this is that every time you write new in your program, you're creating an unmanaged object on which delete has to be called on later unless you want to risk a resource or memory leak. In modern C++, we have smart pointers, which are a class that wraps a raw or bare C++ pointer to manage the lifetime of an object it's being pointed to, and as well the standard C++ container classes that make it easier to ensure that every new will be paired with exactly one delete. And they really are applicable to just about every situation in which you'd want to use dynamic allocation. Now, if you need some weird memory management logic, then you should still incorporate it into an RAII class so that the language itself can help you make sure that the destructor is called, releasing the resources being held. This will make it much easier to write correct code than using new and delete. Pointers, by many, are considered to be the most powerful feature in C++. Now, pointers are variables that contain the address of an object kept in RAM. And they allow you to directly access these addresses and manipulate the contents, but they're very complex to handle. Using them correctly, they improve the efficiency and the performance of your program. But on the other hand, if used incorrectly, you could create even more problems for yourself. Memory leaks, unreadable or unmaintainable code. It can even cause those pesky buffer overflows. So let's take a look at a snippet here. We assume that getFoo pointer is going to always initialize pfoo to either a valid pointer or null. Now, to make sure that getFoo pointer always writes the output, we would have to trace into our getFoo pointer for several function calls. And there are a few steps that we can take to avoid problems with pointers in C++. Now, the first one is don't leave pointer variables uninitialized. Just initialize them when declared. The big concern here is that uninitialized variables tend to take on the values of previously used pointer variables. So if you don't know what to initialize a pointer to, just initialize it to null. The second is that you should always zero out your pointer variables after you use them. The third, allocate your memory from the heap and return the memory block at the same level of abstraction so that you can actually avoid these memory leaks. If you intend to catch exceptions to prevent a program crash, make sure that you catch the exception and then return the blocks to the heap before the pointers go out of scope. When this happens, your memory ends up getting lost. And lastly, just to make sure that your types match, because you don't really need to recast a pointer without specific reasons. A copy constructor is a member function that initializes an object using another object of the same class. So when you pass an object by value, a copy of that object is created, and if you haven't defined the copy constructor, then a member by member copy is performed. Assignment operators behave the same way and invoke when you assign one object to another object. Let's take a look at this pointer holder class snippet to examine the security concern. When we pass one of these to a function, the copy constructor creates a second copy, and we end up racing to see which one will be able to delete the pointer first. The second one is going to cause a double free condition, which is an error that occurs when free is called more than once with the same memory address as the argument. And by calling free twice, there is the chance that one of them is using the object that has been encapsulated within the class. So we're opening our code's memory management data structures to corruption, and this could cause an attacker to execute some arbitrary code. Fortunately, the fix for problem copy constructors is fairly easy. When your class controls resources, declare a private copy constructor and assignment constructor with no implementation. This way, if a class external to the class with your private declaration attempts to invoke one of these, then you will get a compiler error about invoking a private method. If you accidentally call one of these internally, then you'll get a linker error because there's no implementation. Now, the benefit to this is that the compiler will let you know that the class is unsafe in the event that this class is a member of another object that has not declared copy and assignment operators. The standard template library is part of the standard C++ library, and it's just a set of C++ template classes that provide the more common programming data structures and functions. So it's a library that contains container classes, algorithms, and iterators as well. So if you see C-style arrays, character arrays, or other tedious code instead of vectors or strings and so on, then your code probably isn't using the STL. If you haven't spent much time learning about it, or if you're still new to C++, then you really should check it out. It can help you avoid many of the pitfalls that I've mentioned here today. And a great reference book to learning the standard template library is the STL Tutorial and Reference Guide book by David Musser. Here are some other common security practices that can be implemented to help defend your code. Keep your design simple and small. Overcomplicating your code can make it far more difficult to review your code and allows for more human error that leaves you open to attack. Access decisions by permissions, not exclusion. So everyone's heard of this, and this is basically your typical fail-safe defaults, essentially saying that if your permission systems fails for some reason, then your legal access is denied, but the illegal access is also denied. Every access to every object is checked for authority, and design depends on possession of keys and passwords. So your design doesn't necessarily have to be a secret, but have it depend on keys and passwords to unlock. Protection mechanisms should require 2 keys to unlock, not just one, and that each program and each user should have the least set of privileges necessary to operate. As I mentioned earlier, software security is really everyone's job, not just for developers, but QA, design. If you happen to work on documentation, you're just as involved in securing your organization's applications. Here's a great list of books that I utilize to design and build software. Writing Secure Code, The 24 Deadly Software Security Sins, Programming Flaws and How to Fix Them, Software Security, Building Security In, and as well as the 3rd edition of Effective C++, 55 Specific Ways to Improve Your Programs and Designs. Now, we really only covered the tip of the iceberg here in software security. There's so much more to learn and 1,000,001 resources available to you, but most importantly, make it a habit to stay current and up to date with your software practices. If you have any questions, please feel free to reach out at mary.kelly@embarcadero.com.